Today we are here with the module 4 of the chapter 2, which is combination of capacitors. So let's begin this module. In this module there are two kinds of combination of the capacitors, which are capacitors in series and the capacitors in parallel. So first one, the capacitors in series. Let's discuss this. The capacitors in series. Watch here. These three capacitors are connected end to end. When the capacitors are connected end to end, then we say that the capacitors are in series. This is the series combination of the three capacitors with the capacitances C1, C2 and C3. So when we connect this to the supply, what happens? The equal and opposite charges produce in each and every plate of the capacitors. We have provided the potential difference V and closed the key. Then what happens? This plate gets positive Q charge and this negative Q charge. Due to this negative Q charge, this gets positive Q charge and this gets negative Q charge. Due to this negative Q charge, this gets positively charged and this gets negative Q charge. And the excess of the charge gets grounded. Okay, so now each and every plate of the capacitors having equal and opposite charges, plus Q and minus Q, and the potential differences across these capacitors is divided according to the capacitances of the capacitors. Means the capacitances of these capacitors are different, C1, C2 and C3. According to their capacity, the potential is dropped across them, like this. Across C1, the potential drop is V1. Across C2, the potential drop is V2. Across C3, the potential drop is V3. Alright, for C1 it's V1, for C2 it's V2, and for C3 it is V3. And the total potential provided from the source is V. And in this condition we can say that in series combination the amount of charge on each plate of the capacitors is same, while the potential difference across each capacitor is different. We can clearly see here the charges are equal in the magnitude, however the sign are different, but the magnitude is same, while the potential drop is different in each capacitor. This happens in series combination. The charge is the same and the potential difference is different. Now these potential drops are provided from the total potential difference, which is provided from the source. So we can take this like, as we know that Q is equal to CV or V is equal to Q upon C. This is the formula for the capacitance in the terms of charge and the potential. Q is equal to CV, or we can write it like V is equal to Q upon C. This is the formula for the total potential. In the same way, the potential drop across these capacitors will be given like this. Similarly, V1 is equal to Q upon C1, V2 is equal to Q upon C2, and V3 is equal to Q upon C3. Now we will calculate the total potential that is provided from the source, which is dropped across these capacitors. Okay, watch here. Now the applied potential by the source will be given as V is equal to V1 plus V2 plus V3. Put the values of V1, V2 and V3. These are Q upon C1, Q upon C2 and Q upon C3. The total potential which is provided from the source or the applied potential will be Q upon C. Q is the total charge and C is the total capacitance of this combination. Here we need to find out the capacitance of the combination of these capacitors. So how to calculate this? Watch here. Take this Q as common in all these three terms. Right now this Q is cancelled out by that Q, and we will get this 1 upon C is equal to 1 upon C1 plus 1 upon C2 plus 1 upon C3, where C is the resultant capacitance of these capacitors connected in series. So in series combination, the reciprocal of the resultant capacitance is equal to the sum of the reciprocal of the individual capacitances. Alright, so here in this case there are three capacitors. There can be more than three capacitors. So what happens then? Watch here. If there are more than three capacitors connected in series, then the equivalent capacitance will be given as 1 upon C. This C is the equivalent capacitance, and the reciprocal of this equivalent capacitance will be given as 1 upon C1 plus 1 upon C2 plus 1 upon C3 plus 1 upon C4 plus 1 upon C5 and so on. So in the series combination, the reciprocal of the equivalent capacitance is equal to the sum of the reciprocals of the individual capacitances of the capacitors connected in series. Now moving ahead, the capacitors in parallel. Watch here. In parallel connections, one plate of every capacitor is connected to one terminal, and another plate of each capacitor is connected to another terminal, and between them the power source is applied like this. The potential difference V is applied, the key is closed, and there are charges produced like this: plus Q1 minus Q1 plus Q2 minus Q2 and plus Q3 and minus Q3. In parallel connection, the charges are distributed according to the capacitance of the capacitors, while the potential difference across each capacitor is the same, since it is the parallel connection. So this is the applied potential, which will be applicable as same for all these three capacitors. So we can say that in parallel combination, the potential difference across each capacitor is same, but the amount of charge on the capacitors is different. So the potential difference is same. This V will be applicable for all these three capacitors, but the amount of charge is different. For this is Q1, for this Q2, and for that Q3. Now moving ahead, we know that Q is equal to CV. According to the definition, Q is equal to CV. With the help of this, we can write similarly: Q1 is equal to C1V. Q1 is the charge for the capacitor C1, for the capacitor of the capacitance C1, and Q2 is equal to C2V. This is for the second capacitor. Q2 is equal to C2V, and for the third one, this is Q3 is equal to C3V. Now the net charge will be given as Q is equal to Q1 plus Q2 plus Q3. Now put the values, the value of Q, put it like CV, where C is the equivalent capacitance, V is the applied potential difference. The Q1, the value of Q1 and Q2 and Q3 we have decided before. These are C1V, C2V and C3V. Take this V as common from all these three terms. We get this. Now this V will be cancelled out by that V, and we will get C is equal to C1 plus C2 plus C3. So this is the equivalent capacitance when these three capacitors are connected in parallel. Okay, so in parallel combination, the capacitors are directly added to give the equivalent capacitance. Okay, if there are more than three capacitors connected in parallel, then the equivalent capacitance will be given as C is equal to C1 plus C2 plus C3 plus C4 plus C5 and so on. All the capacitors which are connected in parallel will be summed up to give the resultant or the equivalent capacitance. Now moving ahead, we have to find out the energy stored in a capacitor. So what will be the energy stored in a capacitor? We will calculate. Watch here. Take the small work done to move a small charge dq from one plate to another in a capacitor will be dw is equal to v dq. Where does it come from? It comes from here. Since v is equal to dw over dq, this is from the definition of the electric potential. V is equal to w upon q, or v is equal to dw over dq. From here we can calculate dw is equal to v dq. That's we have taken. So this is the small work done to move the small charge between the plates of the capacitor. Now put the value of V as Q upon C. How can we put the value of V as Q upon C? Since Q is equal to CV, and from here V is equal to Q upon C. The value of V is Q upon C, that we have placed here the value of V as Q upon C. Now this is the small work done to move the small charge. Now we will calculate the total work done to move the charge Q. For that we have to integrate this term. We have to integrate this equation. How to integrate these terms or these equations? Watch here. Integrating to get the total work done. Let's do this. Integration 0 to w of dw is equal to C. The capacitance is constant. That's why we are not integrating the capacitance, since it is a constant. We don't integrate the constant. Now this q dq we are integrating from 0 to q. Now the integration of dw becomes w. This lower limit 0 and the upper limit w. 1 upon c as it is, and the integration of q dq becomes q square upon 2. Adding 1 in power, dividing by the new power, and the limits 0 to q. Now put the limits. In the place of w, put the upper limit w minus, put the lower limit 0. Here 1 upon c as it is, this 2 comes over here, and in the place of q, put the upper limit, that is q, with the same power, q square, minus. In the place of q, put the lower limit, that is 0. 0 square remains 0. Now this would be w minus 0 is equal to 1 upon 2c q square minus 0. Solving this, we will get w is equal to q square upon 2c. W is equal to q square upon 2c. Now this work done is stored in the capacitor as potential energy, so we can write it like U is equal to q square upon 2c. This is the energy stored in a capacitor. Now we will elaborate this formula a little bit more. Watch here. Since q is equal to cv, so therefore u is equal to q square upon 2c that we have derived. In the place of q, put this value, q is equal to cv. So this becomes cv whole of square upon 2c as it is. Now this cv is whole of square, so this becomes c square and v square. 1c is cancelled by 1 power of the c, so this becomes u is equal to half cv square. This is the formula for the energy stored in a capacitor in the terms of capacitance and potential. Right? One more formula can be there, or the illustration or the elaboration of this formula will be in the different manner. Let's illustrate that. Watch here. Since C is equal to Q upon V, the same formula we are placing from C is equal to Q upon V. Now take again U is equal to Q square upon 2C. In the place of C, put the value of C as Q upon V. When we put the value of C as Q upon V, it would be like this. Now this Q will be cancelled out by 1 power of the Q, and we will get U is equal to half QV. So this is the formula for the energy stored in a capacitor in the terms of charge and the potential. So we have three formulae for the energy stored in a capacitor in the different terms, and these are U is equal to Q square upon 2C, half CV square, or half QV. So this is the energy stored in a capacitor. These are the three formulae that we have derived for the energy stored in a capacitor. So that's all for now. See you again. Thank you.